So here is again the second principle of mathematical induction, often called strong induction. States the following. So to show that for all n, P of n is true over domain D, which is a set of consecutive integers with some smallest entry. It suffices to show that P1 is true, so that's the base case. And then the induction step, instead of Pn implies Pn plus 1, it becomes P1 and P2 and P3 and ... Pn minus 1 and Pn, that all of those together being true implies that Pn plus 1 is true. And the reason for the second principle of induction, the times when it is used, is essentially when the reason Pn plus 1, well, with the first principle, the reason Pn plus 1 is true is because Pn is true. It's essentially the operating principle or idea with ordinary induction. Step n plus 1 follows from step n. Here, step n plus 1 follows from something that came before. Don't know which one, but one of those that came before. Or two of them that came before. Or something like that. They are logically equivalent, the first and second principles of induction. There's no, logically no difference between the two. It's just in the way that it's used. So the basic example is the following. Every integer n bigger than or equal to 2 can be written as a product of prime numbers. And you consider just a prime number itself to be a product of primes, just as convention to make it easier to say. And the basic way that this proof works, so here's the remark at the end there. Like when you're trying to show that 2100 is a product of primes, the fact that 2099 is a product of primes doesn't really enter into the picture. 2100 is a product of primes because 2100 is not prime itself. It's a product of two smaller numbers, 70 and 30. Not the only two smaller numbers it's a product of, but 70 and 30 are two of them. And 70 and 30, they're both products of primes. So 2100 being a product of 70 and 30 is a product of those primes there. So the way you formalize that idea in the proof is as follows. The base case is 2 itself is a prime and therefore a product of primes. So that's n equal to 2. Remember, 2 is a prime number. It just has the distinction of being the only even prime number. So then the induction step starts at 2. So P2, P3, P4, Pn minus 1, Pn minus 2, Pn minus 1, Pn. All of those being true implies Pn plus 1 is true. And one of the sort of tricky parts of using this is writing down the induction hypothesis. So writing down the induction hypothesis requires you to quantify this here. It requires that statement to be said in some sort of quantified fashion, universally quantified fashion. So the way it works here is, well, Pn, the predicate Pn is that n is a product of primes. That's what we're trying to prove. Okay, so assume that every integer from 2 to n is a product of primes. And now we want to show that n plus 1 is a product of primes. So every number from 2 to n is a product of primes by assumption. and we want to show that n plus 1 is a product of primes. Okay, and from there it goes like this. If n plus 1 is prime, then you're done. The convention is that a prime by itself is a product of primes. If n plus 1 is not prime, well, what does not prime mean? Not prime, well, it means different things, but one way to think of it is that it's a product of two smaller numbers. Right? A prime number is a number that's divisible just by 1 in itself. So you can't write it as a product of two smaller numbers. It's only when you're not prime that you can do that. So if n plus 1 isn't prime, it's a product of two smaller numbers, a and b, where a and b are less than n plus 1 and bigger than 1. So they're in the set from 2 to n. But our assumption is that everything in the set from 2 to n is a product of primes. So by the induction hypothesis, A is P1 to PS, B is Q1 to QT, where each PI and QJ is a prime number. So now n plus 1, being a product of A and B, is a product of its products of primes. And that's that. That's the sort of standard first example you always get. Here's a real nice geometric example. Okay, so let's show that the sum of the interior angles of an n-sided polygon is n minus 2 times 180 degrees for all n bigger than or equal to 3. Right? So however many sides your polygon has, the angles in it, they add up to this number here. N minus 2 times 180 degrees. So 180 for a triangle, 360 for a square or quadrilateral. What's times 3? 540 degrees for a five-sided polygon, so on and so forth. Okay, so the base case here is n equal to 3, and this one has another distinction of being one where the base case actually is not trivial. So why is the sum of the angles in a triangle 180? Does anybody know? So we need to show that the sum of the three angles of a triangle is 180 degrees. What is 180 degrees? What does that angle look like? Of 180 degrees, right, is the rotation necessary for creating what?
Just a line.
Yeah, a straight line. All right, so you got your segment there, and you're going to rotate that segment a certain amount, theta, right? And then when theta equals 180, and you unfold that guy, you actually get a straight line. All right, halfway around a circle. All right, halfway around a circle. So why is it that the triangles add up to 180? The angles in the triangle. Has anyone seen this? Nobody's seen this before?
I haven't, no.
No? So I got my triangle here. And we're going to have three angles. We're going to have alpha, beta, gamma. So there is some assumptions we're going to have to make here. The assumptions we're going to have to make are this stuff about parallel lines cut by a transversal. That they create several angles of the same measure. All right. So consider an arbitrary triangle like that. Extend one side of the triangle into a long line, and then make a parallel copy of that line on the opposite side. So extend one side of the triangle into a long line and copy that line. Passing through the opposite vertex. So here's our triangle. Copy. Like that. So we want to take just one side of it. I don't know if I can isolate one side. No. Okay, so we extend one side of that triangle, whichever side you want, into this long line here. It didn't work. Huh? All right. So all right. Now make a copy of the line. And put it on the opposite side. Like that. And those two lines are parallel. So now we've got a couple transversals here. All right, we've got this transversal and that transversal. Right, and we're assuming this bit about parallel lines cut by transversals creating congruent angles. Opposite vertex, so this yields two parallel lines cut by two different transversal and then therefore we have the angles shown. Right, so this angle right here, oh, that's just terrible. this angle right here has to be beta, right? And this angle right here has to be what?
Alpha.
It has to be alpha, right? So alpha plus beta plus gamma is the angle for a straight line, which is 180 degrees. Right? As required. So this is a nice proof in that it's a good example of one where the base case is not just some sort of triviality. The base case requires some real proof. Okay. So now take P to be, or sorry, the inductive step. So this is that P3 and P4 and Pn implies Pn plus 1. What's Pn in this case? What's the predicate Pn in this case? It's right up here. What's the predicate Pn? What's the predicate Pn? What's the statement, with the variable entry, n?
Show the sum of the interior angles of an n-sided polygon using that n minus 2
Yeah.
times 1 half.
Not to show that, but the sum of the interior angles.
Oh, yeah.
Yeah. So Pn is the sum of the interior angles of an insided polygon is n minus 2 times 180 degrees. Okay, so that's Pn in this case. So how do we write down the induction hypothesis? So assume that for any, what? How did we say it up here? There's a little bit of a twist in it this time. Assume that every integer in the set from 2 to n is a product of primes. I didn't actually refer to the integer. I didn't give that integer a name. Here we can't do that. We can't say assume for any polygon with, some unspecified number of sides between 2 and n has angles summing up to this. I mean, we actually have to refer to it. We have to refer to the number of sides in the polygon. So what letter shall I refer to the number of sides in a polygon? Shall I use n? May I use n? Can I use n?
Yes.
Assume that for any n-sided polygon, And what's the range for n? With n in the set where?
3 to n.
So I'm saying, I'm quantifying n. I'm saying n is some number from 3 to n. Have I double used the n? Have I given the n a double meaning? Come on, guys. Work with me. Have I given n two different meanings, which I can't do?
Yeah, you have.
Right. So you have to refer to the number of sides in the polygon, but you can't use n, because n is what's being used to do the induction. Okay, so assume for any, so you got to pick a different letter, whatever letter suits your tastes. Assume that for any k-sided polygon with k in the set from 3 to n, that the sum of its interior angles is k minus 2 times 180 degrees. Now what do we need to show? Show that any what-sided polygon?
Okay.
So we need to, the hypothesis is, that Pn is true for 3 to n. And we got to show that Pn plus 1 is true. So we need to show this is true. What's Pn plus 1? Right, what's Pn plus 1? Come on, guys. Replace n with n plus 1. And what do I get? We have to show this is true. What is Pn plus 1? This is the function Pn right here. If I have a function f of x is equal to x squared plus 2x or something like that, right, then the function fx plus 1 is equal to what?
X squared plus 2x plus 1.
The function fx plus 1?
Oh, sorry. X
Not,
plus 1.
that was fx plus 1, like that.
Yeah,
Fx plus 1.
Plus 1 squared.
Plus 2 times x plus 1. You replace x with x plus 1. Okay, so here we have the predicate Pn plus 1. The function Pn is this sentence here. Why is the function a sentence? The function is a sentence because it's a logical statement. Okay, so the function Pn is this sentence where you have entry n here and entry n here. So the statement Pn plus 1 is what?
So it changes to n plus 1 minus 2 times 180?
Yeah, but the whole thing is this whole statement. It's a statement of predicate logic. So it's this right here. So I mean, what do I write? What's the first word that I should write? Show that what?
The sum of the interior angles.
Of the interior angles of an what?
N plus 1 sided polygon
Mm-hmm.
is n plus 1 minus 2 times 180.
Right. Is, well, ends up being n minus 1 times 180 degrees, right? So we're assuming, so again, this is an implication statement. How does one prove an implication statement to be true? How does one show that the statement A implies B is true? There's three strategies.
Directly,
Mhm.
contradiction.
And contrapositive. So the direct proof is what? You assume A, right? Show B. So that's what we're doing here. The direct proof. Assume A is true, show B is true. So the A, the hypothesis of the implication statement, is this. So we're assuming this is true. What's that P mean again? What's this P mean? What's that predicate P? What was that again? Guys? I can't see your faces, so I don't know what's on your minds. I need to hear your voices. What does that predicate P, that letter P there, mean again? Right here. That's P right there. And Pn is a statement in predicate logic. Okay, that is either true or false, depending on what n is. And the statement that is true or false is the sum of the interior angles of an n-sided polygon is n minus 2 times 180 degrees. Okay, so was P of 3 true? Did we show P of 3 is true? Do we know that P of 3 is true so far?
Yes.
The interior, yeah, well, that one we proved. That was the base case. All right, so now we're doing the induction step. So the induction step is an implication statement. And we're doing a direct proof of that implication statement. The direct proof is to assume the hypothesis is true. What's that hypothesis called? Starts with I. It's got a fancy name in induction. The hypothesis in the inductive step. This thing here, this thing we're assuming, it's called what? It's the hypothesis of this implication.
The induction
Induction
hypothesis.
hypothesis. Okay. What is the induction hypothesis? It's that P3 is true, P4 is true, P5 is true, all the way up to Pn. All those are true. So how do we say it in English? What was Pn again? Pn is the sum of the interior angles of an n-sided polygon is n minus 2 times 180. So we want to show that that's true. Or sorry, we want to write down a statement assuming this is true for certain values of n. Certain values of n are between 3 and this number n. So since we can't use n to mean two different things, it's got to only mean one thing. You have to pick a new letter to work with. So assume that for any k-sided polygon with k between 3 and n, that the sum of its interior angles is k minus 2 times 180. Okay, so that's the hypothesis. And then in the direct proof approach, you have to show that this is true. Okay, in proofs by induction, one must write these things down. One must write down the induction hypothesis. It must be clearly stated in English, not using symbols of predicate logic. We understand it using symbols of predicate logic, but we have to write it down in English. So we wrote that down. And now we got this conclusion we're trying to argue towards. So you need to know what that conclusion is in English, so that needs to be written down. The conclusion is Pn plus 1. Okay? And that means, in English, the sum of the interior angles of an n plus 1 sided polygon is n plus 1 minus 2 times 180. That's just n minus 1 times 180. All right. So that's what we got to show. So let P, capital P, be some n plus 1 sided polygon. So here's P. It's a little too curvy looking there. Okay, so here's my P plus 1 sided polygon. Or sorry, n plus 1 sided polygon, P. All right. Take two vertices of this polygon, right, and connect them by a straight line through the interior. And connect by a straight line through the interior of P, thus splitting P into two polygons, P1 and P2. So I'm going to take P, which is black, and I'm going to connect two of its sides by a line through the interior, which is going to be red. And now I've got two smaller polygons, P1 and P2. Okay, say that P1 has A sides and P2 has B sides. So what is A plus B? What is A plus B? So P1 has A sides. All of them are black except the red one red one. P2 has B sides, all of which are black except for one, which is red. So P1 and P2 both count the red side. But P1 and P2 share no black sides in common. They share the red side in common, but none of the black sides in common. So if I add A and B, I get what? The number of sides of P or something else. P plus 1? How many times did we count the red side? We counted the red side once or twice? Twice. Right, so P plus 2. But it wasn't P plus 2, it's the number of sides of P plus 2. Thus, A plus B was the number of sides of P plus 2. Not was, but is the number of sides of P plus 2. So A plus B is equal to, how many sides did P have? How many sides did P have? Not in the picture, just, the picture is just for, visual aid. N plus 1, right. So this is N plus 1. Plus 2. So A plus B is equal to N plus 3. All right. Now, the sum of the angles of P1 plus the sum of the angles of P2. Let's take a look. Careful look. Oh, well, before we get into that, so a plus b is equal to n plus 3, and then since a and b are both bigger than or equal to 3, otherwise they won't be polygons. Since a and b are both at least 3, right, this makes a and b elements of what? Which set? What is the range for a and b? Or what is the domain for a and b, I guess? Right. Since a and b are both at least 3, right, then the least a and b could be is 3. What is the largest a and b could be? Each one by itself. Each one by itself. A plus b is n plus 3. And each of a and b is at least 3. So what's the max value for a by itself, and what's the max value for b by itself, if they add up to n plus 3? Max value. Max value. Right? I mean, like, if, you know, if two people have together $10 and one guy has $4 in his pocket, then the other guy's got $6 in his pocket, right? So here we have A and B with n plus $3 in their pockets. But A has at least $3 and B has at least $3. So A and B at most, at least is 3, and at most is what? By itself. At most is what? That's at least. At most. What's the largest A could be? The smallest A could be is 3. What's the largest A could be? A and B add up to n plus 3. Right? And the whole is equal to the sum of its parts. Right? So the whole is n plus 3. A and B, they both add up to n plus 3. A is at least 3. So suppose A was equal to 3. What would B be in that case? N. Suppose A was 4. What would B be? Uh, so 4 plus 1 is 5, right? We need to add up to n plus 3. Or, yeah, n plus 3. 4 plus what is n plus 3?
N minus 1.
N minus 1. Suppose A was 5, in which case B would be equal to
N minus 2.
n minus 2. So what's the largest possible value for B? The smallest possible value for B is 3. The smallest possible value for A is 3. The sum of A and B is n plus 3. Therefore, the largest possible value for A and the largest possible value for B would be what? N. Right, so, I mean, supposing A plus B was equal to 8 or something like that, right? If A plus B was equal to 8 and A and B are both bigger than or equal to 3, then the possibilities for A and B are what? 3 and 8, or 3 and 5, right? 4 and 4. Or if the sum was maybe 10 or something like that, then the possibilities would be like 3 and 7, 4 and 6, 5 and 5, 6 and 4, and 7 and 3. Right, the whole is equal to the sum of its parts. So if the smaller part is 3, then the larger part would be n. Right, here, if the smaller part was 3, the larger part would be 7, being 10 minus 3. So what did we assume about polygons with whose numbers of sides is between 3 and n? What did we assume about polygons whose number of sides is between 3 and n?
It's k minus 2 times 180.
Right. Now the sum of their angles is that much. K minus 2 times 180. So by what? So by the, so what did you just quote? What was that thing called? This statement that you just quoted here, that's called something. Yeah, by the induction hypothesis, right, the sum of the angles of P1, which has A sides, right, is what? So P1 had A sides. The number of sides of P1 is A, so the sum of the angles for P1 is
A minus 1 times 180.
A minus, what was the induction hypothesis? The sum for any k-sided polygon with k between 3 and n. So for any k-sided polygon with k between 3 and n, the sum of its interior angles is k minus 2 times 180. So here we have an a-sided polygon, where a is between 3 and n. So the sum of the angles for this a-sided polygon, P1, is
A minus 2
A
times
minus
180.
2 times 180. And the sum of the angles of P2 is, which has B sides,
B minus 2 times 180.
B minus 2 times 180 degrees. Now, notice that the sum of the angles of P is the sum of, well, let me do it this way. Notice now that why is this thing being so glitchy? So the sum of the angles of P is equal to the sum of the angles of P1 plus the sum of the angles of P2. Because here's P right here, and every angle of P is either an angle of P1, an angle of P2, or it's the sum of an angle of P1 plus an angle of P2. Right? The ones on the red side. The ones on the red side, well, that's the sum of an angle of P1 and an angle of P2. This is the sum of an angle of P1 and an angle of P2. The rest of the angles are either an angle of P1 or an angle of P2 entirely. So the sum of the angles of P is equal to the sum of the angles for P1, which is A minus 2 times 180 degrees, plus the sum of the angles of P2, which was B minus 2 times 180. So this is equal to A plus B minus 4 times 180. What was A plus B? What was A plus B?
Plus 3.
N plus 3. Which is equal to N minus 1 times 180 degrees, which is exactly what we wanted. Show that the sum of the interior angles of an n plus 1 sided polygon is n minus 1 times 180. And that's what we got right there. Okay, that's all for today. Guys, please, you know, there needs to be a conversation here. I mean, I could just whip through the lecture, you know, without having your input as to what I'm saying, but you know, I mean, we need to be talking to each other. All right. So I use this example in other classes too, and you know, I don't get such a silence out of my audience. Okay. So please, next time we'll do something else with the second principle. Okay. All right. So please take a look at this example, and I'll see you next time.